start already. Okay, good morning, everyone. This is our very first talk for 2024. A Happy New Year and advance Happy Chinese New Year coming up later this week. So today is our pleasure to have Associate Professor Ting, right? Yeah. Yuan-sen Ting, yeah, to come here and give us a very interesting talk. As you all know, IDS is supposed to be interdisciplinary, so we cross discipline. This is a truly disciplinary talk today, where we will talk about the language from the sky, which are the stars, and then the language from the earth, which are the human languages, how these two meet together. So Yuan-sen has a very interesting interdisciplinary background. He's received his PhD in astronomy and astrophysics from Harvard in 2017. After graduating, he was awarded a unique four-way, I don't know how you satisfy all of them, four-way joint postdoctoral fellowship from Princeton University, Carnegie Institute for Sciences, NASA, Hubble, and the Institute for Advanced Study at Princeton before relocating to Australia. I know Australia, you can see the stars very well. Sometimes I go there to look at the stars, but I have no idea what they are, but they look very nice. So Yuan-sen also served as a co-chair of the NASA Cosmic Program Stars Science Interest Group and leads Future Spectroscopic Survey as the science group leader. But his research really applies machine learning to advanced statistical inferences using large astronomically sized and astronomical survey data. So he's currently, he's currently Associate Professor in Astronomy and Computer Science at the Australian National University and the Ohio State University. And he published lots of journal papers, many of them on the topics at the frontiers of the Star Trek slogan. I forgot of it, never mind. At the frontier of astrophysics and machine learning. So without further ado, okay. Yeah, without further ado, let us welcome Yuan-sen.
You can hear me, I will just not use the mic. Like, do I have to? Okay. Can people hear me? Like behind? Okay, good. Okay. Let me try my clicker. It works. Okay. Good. For you. Okay. Thank you. Wonderful. Okay. Thank you for the very kind introduction, and thank you for staying here because I know it's Chinese New Year, and this is why I'm here because I'm back, but you are not back. Okay, so I will talk about something that is somewhat a hobby of mine that turned out to be something that I use more and more of my FTE doing. For my real research, you can go to the physics department tomorrow at 2 p.m. So I will talk about like statistics and physics and astrophysics. But today I want to talk about something fun, but also turned out to be more and more important in my research profile, which is trying to understand how we can use like AI to do science. Most of the things that people have been using for the last decade is to build tools to solve some problem in astrophysics. But there's only one part of towards a full AI scientist, right? If you think about how we do science, it's more than just like using tool to solve the question. You also need to come up with your ideas and summarizes the results. And today I want to tackle the former, meaning that like can I use like AI to come up with good ideas, and how do we do that? So let me start by showing you this paragraph. If you are not like an astronomer, it might not mean much to you, but this is an abstract of a proposal that we generated with large language models. So we'll tell you how we get there. But if you are the expert in this topic, which happen to be my own like research topics, then you know that this is actually not a very bad proposal. So if a PhD student came to me like first year and said, hey, I want to work on these topics, I would say, well, sounds like a good idea, and you can try the ideas. So I will tell you how we get there. Of course, most of the things that I will be presenting today are not just my own work. It's work from this group that I lead now called the Universe TBD, standing for the universe is to be decided. They also capture some of the sentiment that we have, which is in the era of AI, how do we try to do science? So who are we? So we are about 30 people, mostly at ANU. It started by my postdoc and myself, and then we bring in more people from the faculty in com science and software engineers, as well as astronomy. And also since the beginning, we know that like we will slowly grow into something quite extensive, so we cannot do that by ourselves. So most of the things that I will talk about, like later, we are working towards with people in the national lab in the US. So some of the projects that we are doing now are talking about 100,000 to 1 million GPU hours. And but we started by working with people that are really the expert in the LLMs from Meta, from UIUC, and also we know that we have to work very directly with the database. Turns out that the main database in astronomy is based at Harvard, so I know them like beforehand. So it's called the ADS, the Astrophysics Data System. And also we are quite glad to be funded by OpenAI and Microsoft Research, and they give us a lot of tokens to let us to use some of the GPT stuff and try to enhance the training. Most of the work that is done is actually done by students, and also most of them are in the intersection of science. So this also speaks to the fact that even though if you want to do the hardcore or research in NLP, you might need to do a CS PhD. But for many frontier science, you can do that as an intersection of science, right? So most of these students are PhD in physics and astrophysics, but they are still able to tackle some of the questions that I will show you today. Before I go into things that we do, I do really want to take a step back, right? So if you think about AI, especially in Asia, we quite often think about AI as a tools, as a engineering tool to solve the question, including computer science. But it's also important to remind ourselves that the fundamentals of computer science is actually come from very, very human based, right? If you read the seminal paper from Alan Turing, the first question that he asked is, can machine think? So since the very beginning, the foundation of CS, the computer science is trying to understand how we accumulate knowledge and how do we mimic the dynamics of humans. And this question was really being pushed away for a long time because the AI was not that strong, right? So if you think about even a chatbot back in the 1966 called the Eliza, which was quite famous. Most of you were not born then. I was not born. Basically, the best way to describe Eliza is like my parents, like your Asian parents, they are very passive aggressive. So if you keep asking them questions, then they will start to attack you, and make fun of you and embarrass you, right? But this, of course, has changed drastically. If you ask the same question to GPT, then it will give you a warm hug that I always wanted from my parents, right? So these are amazing, but with all these very powerful general models, the question is, can we improve on that? And the answer is most likely yes, right? So most of the large LLM now is really, really powerful. But if you look at the earlier version of a GPT or even bots, it's actually not doing that well for science. And Google learned that in a hard way. If you remember, after OpenAI released a GPT, Google released bot, and they want to show an example in astronomy. Now they showed in the presentation, the human asked, well, what discovery can I tell my 9 years old about James Webb? So James Webb is the largest satellite that got just superseded the Hubble Space Telescope that was launched last year. And then the Bart answer, James Webb took the very first picture of planet outside the solar system. This, for non-expert, this seems completely reasonable because James Webb has a very good camera, and one of the main signs is try to do the signs of exoplanets. So if you are like predicting the next tokens, this sounds like a very reasonable answer. The problem is we have took the first picture back in the 1990s, right? So since we have like back in the 1990s, we have like developed something called the adaptive optics, which is kind of like the noise cancelling headset for the turbulences. So you can cancel out the turbulences, and therefore you can image the planet outside the solar system. What happens? Google lost 100 billions in 1 week, right? Because it just showed that the bot is not as good as a GPT. So like at least compared to the earlier version of like GPT or Llama or Falcon, they are generally not doing that well in a very specialized topics, right? Like especially things that are not happening a lot in the corpuses. Corpora. I was told that the plural form of corpus is corpora by the editor. So in the corpora of the internet, there are not many astronomy literature, and therefore it is not surprising that if you're only doing the next token prediction, is not doing that well. And this is where we start to step in. So a lot of the training of a very specialized model do require deep domain knowledge in the field. And this is where the universe TBD try to step in. Since most of you probably have a CS background, so I will not give you some of the introduction of the NLP, but basically to train the models, you need to do two things. One is to pre-train the models, and the other is to align the models or do some prompt engineering. So these are the two things that we have been tackling. Let's talk about the first part, the training the models. So we started by curating the paper. There are about 300,000 papers on AstroPH, the astrophysics portion of the archive. We started by curating the LaTeX sources, which is horrible because the people in the 1990s have no idea what they are writing in LaTeX. So there are lots of bad comments and all these things that we take lots of time to clean that up. And we train on this subset of data. So, and we published the first models back in the September called AstroLlama. So because we train based on the Llama 2 models. And this is still the first and still the only specialized model in astronomy because we don't make money. So no one want to compete with us. So we are still the one doing that. We started by something like really small. It's just like 7B models with the abstracts and try to do text completion. But this is a very small models. We soon realized that this is really bad because it's just like that you have a very small brain. If you further ask the student to read all the astronomy paper, then the student become very inhuman because they do not know how to speak like humans. So we go back and train like another models called the AstroLlama chat. Basically, we extend the data set and also curate like a bunch of Q&A pair in astronomy and train that. This is also a release to increase the chat and Q&A capability. So this is still a very small model, just a 7 billion parameters. Let's show you what we can do, right? So one thing that you want to show is that this do like at least on par with like GPT-4, right? If not better. So even on par is fine because GPT-4 is huge, like no one know how many parameters there are. But if you have a very small models, like a 7 billion model, small, like 7 billion models that can do well in some downstream tasks, then you are saving the earth because it's more green and you can do the same task. So the first thing that we test, of course, is just text completion. And the way we test that is to say, let's say I give you first half of the abstract. Like, can you figure out the second half of the abstract? And this is based on the paper that I wrote with the students. We are looking at what we call the Magellanic Stream. So you have the Milky Way, and next to the Milky Way, there is the LMC, the Large Magellanic Clouds. And in between, there's something called the Magellanic Streams. And people have been wanting to find stars that are bridging these two galaxies. If you ask GPT-4 to complete, like this might not mean much to you, but basically getting about this is like Neil deGrasse Tyson, right? So if you ask a GPT-4 to speak like astronomy, it will just speak very, very generic. It tell you that black hole is amazing, star is amazing, galaxy is beautiful, and you should study all this stuff. But it does not seem to do too well in the specific knowledge. It's unclear if GPT do not know that, or it's due to the alignment. Most likely it's due to the alignment. So the GPT-4 is very powerful, but if you do not give like further prompt, the alignment will hold it back to do very specific answer. And because like you cannot trace the alignment like being done by OpenAI, so this becomes like really hard to force it to do that. But if you compare to the very small models that we train with Astro Llama, it do surprisingly well. So now this is very close to the abstract that we wrote, meaning that if you want to find the Magellanic Stream star, you need to first look for wide field imaging to look for candidates. Then you will compare with the motion of the star to triage the candidates. And then you will go on to look at the spectroscopic study to confirm the candidates. And we also know that Astro Llama does not just memorizes the abstract, because all these numbers are completely made up. But that is good, meaning that it's actually understand, given the context, what you should do, like as a planning, more than just the memorization. So this is nice. And of course, this has makes some good use in astronomy and in the community that people love that. So this is shown in a conference in astronomy where people ask it to write an abstract about assume you are Donald Trump and you write a paper called "Make the Universe Flat Again," and you try to write the abstract for you, right? So these are the models that we released. Of course, we are not stopping there. These are like really growing pretty quickly. So as I mentioned, we started to realize that the 7B models, even though it do pretty well in some specific downstream tasks like text completion, the reasoning is far below what GPT can do. And this is why we keep like scaling that up. So we have a 70 billion parameter model that just finished training. We are testing that now. The reasoning is slightly better. And this, of course, are still something very simple, right? So these are all the path and delta tuning. So we are only fine-tuning part of the parameter in the neural network. And of course, since we have done that, people get interested, and we are working with the national lab in the US now to really do full continual pre-training on the models and even training from scratch. Right, so these are the programs that are ongoing, but this getting like quite expensive because typically this take about 10,000 GPU hours per training. And if you train from scratch, we are talking about millions of GPU hours. Okay, so that's of the landscape, but what we want to try to achieve, right? So there are two things that we try to achieve. Why do we want to do that? One is to trace the past, and the other is to forecast the future. Why this is important? Let's it's fair to say that like academia is broken, like we all know that, and it's broken in a very quantitative way. And this is a paper that I love like a lot. It's a PNAS paper. What this shown here, the dots here are different subfield in sciences, and the x-axis here are the numbers of papers in the corpus of that field, and the y-axis here show you the Gini factors between the papers, meaning that do rich get richer and poor get poorer, and meaning that do the cited paper get more cited over time versus the paper that don't get cited just get like drowned. And this there's a very strong correlation. Also is very aligned with your intuition. As the field get bigger and bigger, no one read papers, so you just like randomly cite papers, and you just recite the paper like every time you write the topics, or cite the paper that your advisor asks you to cite, right? And this becomes a problem because the field get bigger and bigger, and no one can read papers. And your success, if you believe the citation is part of the metric of the success, then your success do depend on luck, right? A lot of or nepotism, if you want, right? So that's become a problem. So the question is how do you solve this problem? Because the field get too big and no one read papers. And no one can read all papers, but the machine can, right? So that's one way to solve the problem. So one way you can circumvent the problem of this like a stochasticity is to say, can I actually cite a paper based on the recommendation from the AI instead of just human citing the papers? But if you want to do that, then you need to make sure that your large language models do understand the papers really really well, because the way that you do that is to extract the embedding from the papers, but you want to make sure that your embedding do understand the nuances in the field, not just a broad brush understanding of the field. And this is another scenario that we can show specialized models do works pretty well. So we are looking at the cosine similarity between all the paper in astronomy. And the yellow band here show you the dot product of the two vectors of the embedding. And the yellow bar here show you what the GPT-3 thinks, right? So basically the GPT-3 thinks all astronomy paper are very similar. They are just astronomy paper. It's just like if you are a layman, then you will just think that, like astronomy papers is about star and galaxy and planets. They are basically the same type of papers. Or put it simply, through the lens of like GPT, all the embedding is actually like focusing on one cone in the 360 sphere. But AstroLlama do able to distinguish two papers that are quite different or quite similar, even both of them are in astronomy. I can show you some examples that actually will make more sense. So these are the two papers that the GPT disagree with AstroLlama. So these are the two papers that, like, even for layman, you can tell that these two papers are completely different. One is on some hydrodynamics of some gas, and the other is on the Coulomb's law. But like GPT still thinks that they are quite similar, right? Because both of them have the words magnetize. So in a way, the GPT, if you do not have the specialized knowledge, you're still doing a lot of keyword search between the papers. But AstroLlama actually know that these two papers are completely different, even though they have the same keywords. So meaning that you have a small nuance understanding of the field. And similarly, you can take two papers that for layman, like this might looks completely different. So one is on the infrared imaging of some nebula, and the other is looking at the ionized region of the hydrogen gas. But both of these is actually studying the same thing, which is star formation. So in GPT, this actually like tell you that this seems similar but not very. But AstroLlama know that these two papers are quite similar. So meaning that you have actually a more nuanced understanding of the papers. Right. So there are lots of fun things you can do, like this is the IDS here. So I will show you some of the fun things that you can do. One is looking at the evolution of the field. If you have all the embedding from all the papers, then you can start to visualize how the field has evolved over time. Right. So this is all the paper they are related to the embedding of cosmology, dark energy, and dark matters. This is quite interesting because this was really popular in the 1990s when you have no data. So the theorists can bullshit their way. So they bullshit a lot in the 1990s. In fact, some of this work actually won the Nobel Prize from Jim Peebles from Princeton. And I think that started to die down over time because you have no data until you have the first data from the Sloan digital sky survey. Then the field become more popular, and then things start to stagnate for some times. And this, of course, is important if you think about broadly more than just the astronomy. Also means that you can forecast, say, the future of a technology or science based on all the embedding from all the papers. You can look at something like James Webb. So James Webb is the largest telescope that costs $10 billion US. You get like people excited, but not very until James Webb get launched. Then the excitement is very high based on the paper published in the archive. You can look at something that I didn't know, like myself. People always say like machine learning is new for science, which is true, right? If you look at like machine learning in astronomy, there is a surge like after the AlexNet, it started to like plateau a little bit. But actually, back in the 1990s, people do use things like MLP to solve problems. Just that no one talked about that. This wave get like forgotten. But now you can read all the papers, then you can start to look at some of these problems. So there are fun things you can ask. Of course, when you have the embedding, one way to do that is to do RAG, right? The retrieval augmented generation. So you can extract, it's like your Google search, but you have a more fine-grained Google search which will help you to summarize the knowledge much better. So in astronomy, we have a very famous journal called the Annual Review of Astronomy and Astrophysics. I think it has an impact factor of higher than Nature. It's like 120, because only the best people get invited to write the review, summarizing the field. There's a reason why this is called the annual review, because if you have something that you want to ask, you need to wait for a year or more before the reviewer can write the article for you. But of course, now you don't need to do that, right? So we have been building a lot of like API to help the community to find the citation, to summarize the knowledge. You can we build things on Slack that you can use Slack. So if your postdoc have any question, and just wake up and say, oh, I want to study the oldest star in the Milky Way, so that it will just summarizes for you and give you all the references. We also have the API that summarizes all paper in astronomy every day for you. We are turning that into a podcast, your daily podcast, that you can like adjust the length. So depending on how long, I don't know, from Buona Vista to here, you can like adjust the length and listen to it. So these are all fun things, but that's not what we are after. So this is tracing the past, like help you to do science more effectively. But ultimately, what we want to do is really to forecast the future, right? Can you really have an AI to do science end to end all by itself? Like this might seem like a bit fancy, but you really need to do step by step, right? So one thing is like, can it come up with very good idea? So can it generate robust scientific hypothesis? And this is more than just next token prediction. And this is the second part that we work on. So more than just pre-training a big models with millions of GPU hours, but we are also doing a lot of prompt training, prompt learning to see what we can do in terms of coming with good ideas. So we have the whole program we call the Hypogen. You might not get the joke if you're not the astronomer, because hydrogen is the most prevalent elements in the universe. So we have a program called the Hypogen hypothesis generation. There are a few bits and pieces that we have been publishing, but it really quite well summarizes in this schematic plots. So how do you judge a hypothesis is good? The first one, of course, you need to make sure that you just don't bullshit, right? You do not hallucinate. And that is quite simple because we have built the RAG system. So you are doing the retrieval augmented generation. So you're retrieving information from real papers and try to come up with good ideas. So that is simple, but just being able to summarize the knowledge, that does not mean that you are a very good a researcher, right? So you can be a student that read all the papers, does not mean that you do quite well. So how do you go from a student to be a professor? One thing is that you need to know how to bullshit your way, right? So you know how to make your idea sounds more coherent, or in a more beautiful words of saying your idea seems more fluid, right? So we have been asking how do we make the generation sounds more fluid? And we tried the different ideas, but since the adversarial critiquing is actually quite good. So like adversarial prompting just means that you have two bots, one to generate the ideas and the other serve as a referee to criticize the idea. So you let them talk to each other. So in the beginning, I show you this paragraph. This is actually the output after a few iterations. So when it first I proposed the idea, it will be criticized by another large language models. And the large language models will also have the information from the vector database. So it will tell you that your idea is not good because blah and blah, and someone has studied that. And in fact, it's important that you are pointing out the references, why your weaknesses, or where your weaknesses is. So it's not only coming out with next token, but it's doing a retrieval to tell you what might be your weaknesses in the proposal. It's actually through like a few iterations that this works much better. And we know that this adversarial like critiquing is important because we ask human to grade the proposal. So what we are showing you here, x-axis is the context length, the y-axis here is the human score. So the dark green here are the one without the referee. You can think about this as dark green is a grad student in the wild. So they just like read papers themselves and think about like ideas. It does not help, So if you have no like supervisor, then you can read as many papers as you want, but your score get like pretty low. But if you do the adversarial like critiquing, actually the score will improve like, over time. So the adversarial like critiquing, at least you will come out with more fluid a proposal. And one thing we do realize is that even with the adversarial critiquing, it gives you more fluid like answer, but it does not necessarily mean it's more creative, right? The creative part is very hard because, and we keep asking ourselves, how do I come up with very creative like ideas? And the best way we can like, mimic that is to mimic the workshop scenario. So we have a generator that will generate a bunch of short conversation in a workshop saying, like, I have this idea, like give me three sentences to criticize that. So I will collect like 3,000 conversation from a workshop setting. I go home and then I run a tournament. I will grade my ideas, right? And the idea is also graded by the LLMs, right? So this is the way that we believe very creative like ideas come from a shotgun approach. So you can create many short ideas, and hopefully one of them is actually quite good. This is super expensive. So like one run here costs about 7,000 in GPT-4 tokens, but we are supported by Microsoft, so who cares? So we just run. And it works pretty well. So if you do this like shotgun approach and genetic algorithm to evolve your ideas. So this is very preliminary, but we have this A/B test, blind test. We have the hypothesis that is generated by this shotgun genetic evolution approach. You have the real proposal. You have few shot and a zero shot from GPT-4. From all the tests that we have done, from all the people, the hypothesis has a win rate of 100%. So it's better than few shot. It's also better than the proposal that we have written. So I should say that most of this work that I show you is have been done in the last 4 months. So things are evolving really, really fast. It turned out to be a hobby of mine. Turned out to be like snowballing like really quick. So where do we go from here? So there are a few things that we are doing. One is benchmarking. The good and bad thing about science is that we have no money, so no one benchmark for us. So we have no ground truth, right? So we have to do that like all by ourselves. We are the CEO, the CTO, the CFO, and everything. So we are benchmarking the own thing. So we are curating the Olympiad question. Turn out that I am guiding the team in Malaysia. So I have some insights. So we are curating the question from Olympiads. And even like GPT-4 is actually not doing very well. It get like 40% or 30% correct. Interestingly, like GPT-4 actually do worse if you do a chain of thoughts. It's just like, say something and then you just lost it in own logics. So there are lots of things you can improve on, even for high school astronomy Olympiad question. And this should not be too surprising because people have been doing that for math in Olympiad. Like it's the same problems. We are curating a bunch of golden Q&A because we have very textbook-like. So this is one good thing about astronomy. We do have the authority review articles. So we can curate a bunch of Q&A, and we are planning to release them and let the expert to put the human in the loop to improve the golden Q&A. So we have done that because we were training the Astro Llama chat. We are going multi-model because you want to read papers more than just a text. So we are working with people in CV, in ANU to look at training like Astro Llama and also learning how to generate a more complete captions to do the retrieval. Interestingly, astronomy is one of the very community where people are super OCD. So we have curated all the astronomy talks. So these astronomy talks are all professional seminar-like talks, and there are 25,000 of them. We have like one archive. We do not know what to do with them, but it's there. So where do you go from here? So we talk about this is my pet project to come up with good ideas. But if you want to have an end-to-end like astronomer, then you need to use the LLM to use the tools like as well. So this is the mixture of experts. So some of us are also expanding on not only coming up with the ideas. So once you have come up with the ideas, write the codes, download the data, do the analysis all by yourself, right? Actually, this works. So I have a student now in Microsoft that is doing very simple question, but basically the level of question that we can do end to end now is like a summer project for an undergraduate. So you can do end to end, come up with ideas, download the data, and analyze the data, write the paper, and put that on archive all by AI, right? No human is involved, right? Kind of yes, but you need to like engineering the shit out of it. It's not like just write a prompt and it works. But this is really kind of the future that we are envisioning, right? So there's no doubt that I hope like this is a very quick talk, but I hope to convince you that there's no reason to believe science will not be done by AI, not in 10 years, probably in 2-3 years, right? Science will be done by AI. The sky is the limit, right? And this is a very scary thought because I know if I stop here, then I will be bombarded with the question about, should we do that? So instead of being asked and answer the question, let me give you my take, the philosophical takes, right? Should AI do science? We know that AI can do science. The question is like, should we let them do science? The closest analog that I can give is chess, right? So I play chess, I still play chess. I remember a time where most of you were not born yet, where Deep Blue beat Kasparov. And the media is like, oh my God, like who play chess anymore? This is over, the chess is done. But we are like 30 years, like 25 years after that. I would say that chess is actually getting better over time, even though human cannot beat chess. Right? And this is very analogous to science. Science is really a very fun intellectual activity. It's not a job, just like chess. And therefore, and this is a very simple job. It's actually, you can envision that science can be done by AI. But even that, human will still do science, just like humans still play chess. And in fact, it's a better world because I remember now, there are lots of like GM from Singapore, which were not possible 10 years, 20 years ago, because like 30 years ago, you need to live in like Soviet Union to be the world champion. But now you do not need to do that because your AI is as good as all the best GM in the world. So you can work with your AI. And this will become the same thing for science. This meaning that a lot of things that will turn out to be very expensive for a country to invest become much more tangible to invest. Right. So in the past, like you might ask, why would Singapore do astrophysics? I cannot hire 20 people in astrophysics to build a department. The question is, the answer is that you do not need to do that. Now, individual astrophysicists can do best science individually at home. And you do not need to build a very big department, right? So this leads to a question of, well, AI scientist is amazing, but why do you want to do astronomy? Right? Like you don't make money. Why do you have to do that? Why start with astronomy? Let's start with the obvious point. No one's died. If you do the hypothesis generation in biomedical, it comes with many ethical things that you need to explain yourself. But in astronomy, if you come up with the wrong hypothesis, who cares, right? So you redo that, right? This is not something that you can do in the other field. Also, astronomy is really, really open source. This is surprisingly, I'm not sure that people know that. So you yourself can download the data from James Webb now. Even though US has spent $10 billion to fly the satellite, most of the data are public right away. And we have the policy of having an open sky. There is less tension between China and US and all this bullshit, right? So it's a very open source thing. And not only open source, we have the habits of making things in something that you can adapt. So there are lots of API that you can like plug. So this is why we can already do some of this like simple science, like end to end, because we have all the API, right? And we are technically savvy. I'm sorry for the biologists, they are terrible in coding. So if you look at their code, they are like R and all this like craziness. We don't do that. We writing in Python. It's well documented and you can plug in. And also, if you want to answer the question that Alan Turing asked, so one of the fundamental questions in computer science is understanding how the knowledge is being accumulated, right? And there are very few fields that can do that, because most of the subfield in physics has a very short time span. Think about nuclear physics, like Oppenheimer solved most of the question. So it was popular in the 1920s. And then it dies down in 20 years. Same things for, I don't know, like particle physics. It was really happening in 20 years ago, but things like start to die down because you solve all the questions that you could solve with your money, right? Astronomy turns out to be a field that is just long-standing for various reasons. I can give you a full lecture why this is the case. But first is the older side, but even you look at the modern astrophysics, it has been very, very active since the 1960s until now. So if you want to show that you can auto-regressively generate knowledge, this is the best field to look into, because we have a long time baseline and you can prove your ideas, right? So this is me in the future, and thank you. I will take our questions.
Interesting talk. Any questions from you?
Thanks for the informative talk. I think you mentioned something about LLM being arbiter to solve the digitization problems. I just wonder like how that gets done, because if you think about the context, if a paper gets like cited more frequently,
right,
probably it's going to play a more important role in the training.
Yeah, so that is a very I don't think that will necessarily bias the citation that way, because you are still citing based on the semantic, right? So it does not mean that it's true that some paper get more cited more, so the field become more popular. So we think that it's like it's like your semantic growth become stronger in that part, but actually within that domain, there are many papers that you could cite. And what we try to do is to do the nearest neighbor like substitution. So, and it's more subtle than that, because like sometimes you cite a paper not because of the entire papers, but because of certain methods. So actually, this is a project that I plan to work on this as my free hobby during Chinese New Year. You can do a lot of RAG, and just try to do the reasoning with GPT to try to figure out a proper way to substitute that. But it would bias the overall training, meaning that it's very easy to imagine Llama is more stronger in, I don't know, like cosmology than some very niche topic in astrophysics. But within that domain, the goal is to substitute the other citation. Yeah. Yeah.
I think two related questions. Well, one is that when I think about astronomy, I subscribe to what John has said, right? I'll be staring at the stars.
Yeah.
So because of that, I thought that there'll be a greater use of images like when you mentioned about multimodal, instead of resorting to the papers itself, right? I thought all the knowledge is in images. So what am I missing?
No, so first, astronomers don't use like telescope like anymore. Right? In real life, we are just like startup company, because like all data are being like collected by big government, and then we just like sit there, like on our bin bags and just like download data and do the modeling. It's true that most of the information are in the data, and this is why we are building the mixture of expert to query that. You can think about this like, to the baseline, you have the LLM as the interface, right? You come up with the ideas. What should I look into? There are so many things you can look into, but what should I look into? But there are a lot of knowledge there's also can be done by just looking at the papers. And this is something that is not really well, like even nowadays, we are taught to students, they have the same impression. I want to play the data. But some of the most famous astrophysicists, they might not seen a photon in their real life. They just read paper and write papers. So there are lots of knowledge within the paper that you can extrapolate. And this is also a very a unique thing about astronomy, because astronomy is a very broad field, and most of the time we are like trying to link the ideas. Because if you want to understand the evolution of the galaxy, you need to understand the physics of the star, you need to understand the interstellar medium, you need to understand plasma. And all these you need to have a very broad understanding of the field. So there are lots of very good theories. We make jokes that they never seen a real image in their life, but they are still the biggest astrophysicists. And one of the examples is called Joseph, who is a professor at Oxford. I work with him. He this person that he never read data, right? He just read a lot of papers. We just how do I think like Joe? Yeah, so there are lots of knowledge within the papers.
Right.
Yeah.
Okay. Then the other one is, what's the situation like for publications, right? For astronomy, are most of them behind paywall, and then do they allow you to put on archive? The reason I ask is because if the really good ones are behind paywall.
So this is another good thing about astronomy, like 99% or more of the paper on the archive. Even though the publisher are making us really sad, because I just get a paycheck today from Nature. It's like 15,000. I say if you pay 15,000, you can put that on archive. If you don't pay the 15,000, then you can also put that on archive, but after like 6 months. Yeah, but luckily this is another good thing about astronomy. 99.9% of the paper is on archive, right? And this is very different. I'm surprised, like geophysics, right? Because my colleague at ANU say, hey, I want to work on this for geophysics. I'm like, okay, yeah, just download the data from archive. And they say, no, like most of the good paper are in this like secret computer in Russia. I'm like, I cannot do that, right? So like if your paper is not like complete, yeah. So this is also very unique just because we don't make money, so no one care, and all the paper and data and tools are all online. Yeah.
Thanks for very nice talk. About reading the ideas, I have some questions. So, like in realistic scientific research, even an idea, if I know whether it will work, if I know it will work, normally that idea can be a little bit trivial.
Yeah.
Right? So many impactful ideas at the beginning can be seen very uncertainty.
Yeah. So this is a very good point. This is exactly what we are doing now with like Microsoft. So it's exactly because in astronomy we have the same problems where you don't want your PhD student to work on a project that could win the Nobel Prize, but 99% of the time, like it will fail. Instead, you want the student work on, like look at these images and just do the basic, the median research, because the cost is very high. So the advantage of having AI scientists end to end is that you can let the bot to do things that you would not assign a student to do. Those high risk, high reward project. Right, and that is exactly what and this is very unique for astronomy. The astronomy is to understand the universe, meaning that there are like infinite questions that you could ask. This is very different from solving cancer or particle physics. You have like one goal, and astronomy is like you can take any object and you try to understand how this thing works. And a lot of projects, like 99.9% of the project, just never get tackled because they are either not mainstream or they are too outlier. Like it's either you get tenure and they work on those projects, and then like usually you get tenure, then you don't do science anymore. So that's the problem. Yeah.
So I'm curious about the one where you have the LLM playing with the other one, where I'm just wondering whether you're exactly using the same one, because if I'm the one generating the ideas, I would sort of naturally, score them very well.
Yeah.
Right? to generate?
Yeah, so this actually is we work on this project all independently. So both of them is actually GPT-4 here. But it's true that we want to like substitute that, say one with Astro Llama and one with a GPT-4 and train that with like different downstream tasks.
Right.
Yeah. So that's a very good idea. Yeah. Yeah, each of these slide will be a thesis by itself. Yeah. Yeah.
I have two problems. So the
Yeah.
first one is regarding evaluation.
Yeah.
So basically, how do you think about evaluating whether you cannot done something good?
Right.
Because I think now it's extra llama is just
Yeah. No, so we are now training on all the first version is on the abstract, but the rest is on the whole sources.
The past seems to be more like this.
Yeah.
What I thought maybe developing better metrics for maybe evaluating whether it's
Yeah.
But the question is, you think about the time tree.
Yeah.
And I saw that you also use quite a lot of rank.
Yeah.
So actually, how do you compare these two? Like, could you get the same performance using just rank? Or
Yeah.
is something?
Yeah. I can start with the first one first. The benchmark is like really a pain and really no one how to do that. So I just sent a student to the Argonne lab exactly to do that. So this is a very broad question about you have like different tasks, right? You break them down to different tasks. One include like planning. So we know that if you use like GPT, the planning is very important, like instead of just a general prompt. But even the planning, you have no ground truth, right? The different people do the research in different way. And that is really, really tricky. So like planning, like how do you grade that? You can grade that with like GPT, but then it's like, your like it's a cyclic logic. The Q&A is easier. So these are two benchmarks that we are building. We are building three benchmarks. I didn't show one. So one is on the Olympiad, so that I have ground truth question. But to be fair, like the best like the Olympiad question student might not become the best astronomer. Quite often they are anti-correlated, right? So you can test it on that. You have the ground truth, but then what does that mean, right? Does that mean that it's good for research? It's unclear. We have the golden Q&A, so this might be better. But even that, you need to grade that by a models, right? How close your answer is to this. This can have some serious ground truth because you can, I guess like all physicists have big ego and they love to correct your answer. So I'm pretty sure once I release this golden answer, then we'll start to like criticize. That's good, right? So I will improve the answer. So we are creating a bunch of really high quality Q&A. And these Q&A are on the frontier question, right? So that can be done. And then the rest is we also do some basic thing people do like NER and clause. But those things are testing some of the concept, but not that you can probe bits and pieces of the idea and you can quantify that. But how do you, as you say, how do you know this bot is actually coming out overall a better hypothesis? It's hard. And most of that still relies on human like grading. But human grading is me and my friends, right? So and my colleagues. You have a very strong bias on that. And that is hard. So I don't know. I don't have a good answer to that, but yeah. So the second question, the GPT and RAG. You want the honest or not honest answer? The honest answer is that after I spend like 100,000 and we are spending still like upgrading with the national labs, the answer is that it's really hard to beat like a GPT plus RAG. So you can do pretty well, like compared to like a GPT raw, like Astro Llama beat like GPT raw, but GPT plus RAG is very hard to beat, right? You can do Astro Llama plus RAG. Is meaning that like GPT know a lot of things, just that how do you pull them out, right? So this is why, we have a lot of. Is that recorded? So it's recorded.
You want
No, it's not really that sensitive, but I do feel that you can do a lot with GPT. So you do not need to necessarily pre-train a model. Pre-training a model is fun for me because it's just me, like I want to learn this field. I know nothing. I just want to learn, right? So my background in AI and do science, I do like CV a lot to analyze the data, spectra, like time series. The NLP is something that I have not played a lot. So for me, I learned a lot about all these like terms and all these things. But I think GPT is the way to go if you have no money. Not you still need a lot of money to buy the tokens, but it's much cheaper, and you can easily fine tune based on the GPT responses, fine tune some smaller models. And that also works really well. So even not Llama, right? You can just use like GPT-4, like create some downstream like answer that you want, fine tune a GPT 3.5, and it generally works pretty well. But I think it's still worth to do the specialized model. It's still like contradicting what I say the whole talk. Because you never know, right? Because if you train like all on the astrophysics for, I don't know, like 100 million GPU hours, maybe the astro Jesus will descend and solve astronomy once and for all. It's always possible, right? It's worth pushing that. Just like like no one push like GPT like in the beginning. You never know. But for now, if you have no money, just do like a LGBT plus RAC, and that's fine. You can do a lot.
So I have one question. So if you look beyond just astrophysics, right? So I guess maybe another science will be medicine, right? So medicine also has lots of papers and all that. So can we do the same for medicine? Yeah,
people do that a lot, right? So this is not unique, right? So biology is a bloodbath, right? You know, LLM for biology. Astronomy is like soul peace, peace and love. Like biology is like.
My loaded question is astrophysics simpler than medicine?
No, it's more difficult, but just like we don't have. No, it's true. Like physics is.
People have thought the astrophysics, but the medicine, well, maybe the medicine people are not so smart. But anyway, so
that's also a true statement.
Like for my collaborators, but yeah, okay.
But I think there are both important questions, but astrophysics, if you have people, you can move much faster because it's open source. You have no ethical problems. Oh, by the way, if younger people that do not know what this is, like this is called Jurassic Park. If you're too young to know.
So what for the PhD students here doing maybe LLMs and all this, what is the, is it all done already? Is there, I mean, from your perspective, what are the research problems?
Yeah.
What are the gaps?
No, I think people are moving in the direction that I think are already moving, right? So that's smaller open source models. Just that.
But you say you should all use the ChatGPT.
Right, but no, I mean like ideally you want to really close the open and close models gap, and there's still a huge gap like between what the GPT-4 can do than the rest of the models, and that's like surprisingly depressing because like basically like they know something that we do not know, or I don't know, like alien give them the random seed to train, and just is surprisingly good, right? And you can have a lot of resources, you just cannot reproduce as good a reasoning capability of like GPT-4. I think the future, not the future, the next few years will be smaller models, open source, but do well in individual like downstream tasks. But people are walking back now because it's too expensive to do the closed model. Yeah.
So I have one last question if nobody is asking anymore. Okay, so tomorrow you're giving a talk at physics, right?
Yeah.
So are you going to tell all the physics students to come to computer science and do a PhD in computer?
I think they should. I mean, like they at least should have like some understanding, right?
So is there still life for PhD in physics?
No.
Okay, then. I think with that, we close. You can talk to professor in private. Okay, thank you.